In this video, I want to talk about the reaction quotient. However, in the last video, we learned about these Keq equations, this equilibrium constant, and we learned every single reaction has its own equilibrium constant. And this equilibrium constant is simply just a number that describes the reaction at equilibrium. For example, let's say, how do we find the Keq of this reaction? Well, we know we use this equation, and we talked about how we use this equation. We take the products and we put them over the reactants. Then again, we need to know the balanced equation. We need to know the balanced equation so we can put these products to their respective powers, and we can put these reactants to their respective powers. But again, we talked about this in the previous video. So again, how would we do this and find the Keq of this reaction? Well, again, we would have this reaction and we would have some kind of initial conditions. Maybe we would have 3 molar of this guy. Maybe we would have 3 molar of this guy. Maybe we would have 4 molar of this guy and 2 molar of this guy. It doesn't really matter what the initial conditions are because we know this reaction will react. It will react and these concentrations will change. And eventually this reaction will react and eventually this reaction will reach equilibrium. Eventually we'll reach equilibrium where the concentrations of these reactants and products aren't changing. And then once we've reached equilibrium, it's those concentrations at equilibrium. It's those equilibrium concentrations of these reactants and products that we plug into this equation. So again, that's the proper way you use this Keq equation. You let this reaction react and you let it reach equilibrium. And then it's those equilibrium concentrations that you plug into this equation. And then when you plug in those values, you get your Keq, your Keq or equilibrium constant. So let's say this reaction happens to have a Keq of roughly 100 over 1, so roughly around 100. So what does that mean? Well, we learned about this in the previous video. This means once this reaction has reached equilibrium, there are relatively much more products relative to reactants. We know this numerator are the products and this denominator is the reactants. So we know we let it reach equilibrium, we plug in those concentrations, and we get this huge ratio. So that means at equilibrium, there's relatively more products relative to reactants. So at equilibrium, there's relatively a lot more products relative to reactants, and when we plug in those concentrations, we got this huge ratio, and that's what the Keq, that's what this Keq number tells us. It tells us about the reaction at equilibrium, and it tells us that there's relatively more products relative to reactants at equilibrium. And if we have a large Keq, a Keq that's much larger than 1, then at equilibrium there's relatively more products. However, so what's this Q? What's this reaction quotient? What is the reaction quotient of a reaction, and what does this reaction quotient tell us? Well, you can find the reaction quotient of a reaction with the exact same equation. It's the exact same equation. We take the products and we put it over the reactants. Then again, we put them to their respective powers based on the balanced equation. However, the difference is when using this Keq, you plug in the equilibrium concentrations. We have these initial concentrations, we let them react, we reach equilibrium, and it's those equilibrium concentrations that you plug into this Keq equation. That's how you use this Keq equation. You plug in the equilibrium concentrations. Once we've reached equilibrium, you plug in those concentrations to this equation. However, this reaction quotient is different. It's different. Rather than plugging in the equilibrium concentrations, this reaction quotient gives us a snapshot picture of where the reaction currently is, the current conditions of the reaction, the prevailing conditions of the reaction. For example, let's say we have this reaction, and let's say we have 1 molar of this guy. Let's say we have 1 molar of this guy. So we have 1 molar of these reactants, and let's say we have 1 molar of these products. So we have this initial, this current condition, this prevailing condition. We're not at equilibrium because we know when we're at equilibrium, we have relatively more products than reactants. At equilibrium, we have a lot more products relative to reactants. So if we have 1 molar of all reactants and products, we're clearly not at equilibrium. So we have these current conditions, these prevailing conditions. So when using the reaction quotient, you plug in these current conditions, these prevailing conditions. It's these concentrations that you plug into this reaction quotient. So these are the initial, these are the prevailing current conditions. It's those concentrations you would plug into this equation. So we could find the reaction quotient of this reaction at this particular instant, at this simultaneous, this moment. These concentrations, with these concentrations, we could find the reaction quotient of this reaction at this moment by plugging in these concentrations. And if we were to plug in 1 molar concentrations to all these reactants and products, we would get a reaction quotient of 1. Because again, 1 times 1 squared is just 1, and then again 1 times 1 squared is just 1, so 1 divided by 1 is just 1. So this reaction, this current conditions, these prevailing conditions, this reaction has a reaction quotient of 1. And again, this reaction quotient tells us where the reaction currently is on its way towards equilibrium. Because we know once we've reached equilibrium and we plug in those equilibrium concentrations, we get 100. But with these current conditions, we get a value of 1. So therefore, the reaction quotient doesn't equal the Kq. The reaction quotient is 1 when we know the Kq is 100. So therefore, we're not at equilibrium because the reaction quotient doesn't equal the Kq. And again, so this tells us we're not at equilibrium, and it tells us this reaction is on its way towards equilibrium. It's not currently at equilibrium, but it's going to keep on reacting until it reaches equilibrium, and then once we've reached equilibrium and we plug in those concentrations, then that's when we'll get 100, and because we'll have relatively more products than reactants. But here's a really neat trick. This is really neat the way this works. But essentially what you can do is you can create a number line. You can create one of these number lines. So we create a number line, and what you do is you put, if this reaction we know has a Kq of 100, so this represents the equilibrium constant. So we would put this equilibrium constant, this numerical value of the equilibrium constant, in the center of this number line, because this represents the equilibrium. This represents when we're at equilibrium. So you create a number line, and you put the Kq in the center of the number line. And then you can take any arbitrary concentrations. Plug it in and find the reaction quotient at these arbitrary concentrations and find the reaction quotient. And then you take the reaction quotient and then you plug that into your number line. And we know because our reaction quotient is 1, it's less than the Kq. It's smaller than the Kq, so therefore the way number lines works, the convention for number lines, is the smaller numbers go to the left, and then it gets larger as you go to the right. So therefore what you do is you take the Kq, you always put that in the center, and then you find, based on the initial condition, the prevailing conditions, you find the reaction quotient. And then once you find your reaction quotient, you put it on the number line. And because the reaction quotient was less, it would be to the left of the number line. So now this is where the magic occurs. Because the reaction quotient is to the left of the Kq, but we know this reaction quotient wants to get to the Kq. We know these current concentrations want to reach equilibrium. They're on their way towards reaching equilibrium. So we know this reaction quotient, these current conditions, wants to reach equilibrium. It wants to reach equilibrium, and these concentrations are going to change going to it. So it's changing in a way going towards equilibrium. So therefore, this is where the neat trick occurs. Because the reaction quotient was less than the Kq, you know the reaction quotient is going to the right towards Kq. Because again, we see in our number line, the reaction quotient is less than the Kq, so therefore the reaction quotient is going to the right, going towards Kq. So therefore, we know our reaction is going towards the right. Because we know on this number line it's going towards the right, so therefore we know this reaction is going towards the right on its way towards equilibrium. And again, that makes sense because we know at equilibrium, we already explained at equilibrium, we have a lot of products relative to reactants. So we know at equilibrium, we have a lot of products. So therefore, this reaction is going towards equilibrium, and as it goes towards equilibrium, it's going to go to the right to create more products. And as it goes to the right and creates more products, then our reaction quotient will have more products relative to reactants, and the reaction quotient will slowly increase. As this reaction goes to the right, we create more products. So therefore, we're creating more products, so this reaction quotient of the products will increase, and it'll keep on going to the right until we've created enough products where we're at equilibrium. So that's what's neat about this number line trick. So let's do another example. Let's say maybe that was a little complex. So let's do another example. Let's say these are our initial concentrations. Let's say these are our initial concentrations where we have 10 molar of CO2, 10 molar of water, and 1 molar of these guys. So if we're in this situation, we know we can find the reaction quotient. We can find, based on these current conditions, these current prevailing conditions, we plug in those current prevailing conditions, we plug them into this equation, and then we'll get our reaction quotient. And if you were to plug in this 10 molar here, and you were to plug in this 10 molar here and square that, and then divide it by this 1 molar divided by this 1 molar square, if you were to plug in all those values, you would get a reaction quotient of 1,000. We would get a reaction quotient of 1,000. So now, again, we can use our little number line trick. we know the Kq, which is 100, we put in the center, and then we find our reaction quotient. So based on these current concentrations, we have a reaction quotient of 1,000. So now our reaction quotient is larger than the Kq. So now our reaction quotient will go to the right, because again, that's the convention for number lines. The larger goes to the right. So now based on our reaction quotient now what can we determine? Well, we know our reaction quotient isn't equal to the Kq, so clearly these concentrations were not at equilibrium because our reaction quotient doesn't equal the Kq. But again, we can use this neat number line trick, where we know that the reaction quotient wants to go towards equilibrium. We know this reaction quotient wants to go towards equilibrium, and we know these concentrations will change, so we go towards equilibrium concentrations. So therefore, we're not at equilibrium, but we know the reaction quotient wants to go towards equilibrium. So therefore, this reaction will go to the left. The reaction quotient wants to go towards equilibrium, so therefore wants to go to the left. So therefore this reaction, these current conditions with this reaction quotient wants to go towards the left. This reaction would want to go towards the left. And as based on these current conditions, it wants to go towards the left. And as it goes to the left, it's going to create more reactants, and therefore it's going to create more reactants. And as it goes to the left, which we saw goes to the left, so as it goes to the left, it creates more reactants. And as it creates more reactants, this value is going to slowly decrease until we eventually reach 100. So the point is this reaction is going to go to the left, and it's going to keep on going to the left until this reaction quotient eventually reaches 100. And then once it keeps going to the left where this reaction quotient reaches 100, then we're at equilibrium. So this number line trick is just a neat way to determine which way the reaction will go. If we have current concentrations that have a reaction quotient that's larger than the Kq, you know the reaction will go to the left. However, if you have initial concentrations where based on the initial concentrations, maybe we have these initial concentrations. If you have other initial concentrations that you plug in, and you plug in these initial concentrations to the reaction quotient, and you would get 1. So in this situation, the reaction quotient is less than the Kq. The reaction quotient is less than the Kq. So in this situation, you know the reaction quotient will want to go to the right towards equilibrium. So then in these reaction quotient conditions, this reaction wants to go to the right towards equilibrium to create more products. And as it creates more products, this numerator will increase eventually, and we'll keep on creating more products until this ratio reaches 100, and then we're at equilibrium. So again, this reaction quotient just tells us a snapshot picture of where the reaction currently is on its way towards equilibrium.